Okay, to study mathematics in general, we need to understand some basic logic. And in this video, I will informally introduce some formal logic. So let's start. The basic building block of formal logic is called a proposition, which is any statement that can be either true or false. Proposition. This can be either true, which we denote by this symbol, or false. In this lecture, we use this symbol to represent the false value. And these two values are called truth values. Okay. For example, Dr. Akira teaches at University Brunei Darussalam is a proposition. It's either true or false. Or the truth value of a proposition may not be known sometimes. So, for example, the Goldbach's conjecture, that is, any even numbers greater than 2 is a sum of two prime numbers, is a proposition, which is either true or false, but the truth value is so far unknown. So far it's been pretty simple, I guess, but we can compose two propositions to form a new proposition. For example, we can combine two propositions by something called logical AND. Let's say P is a proposition and Q is a proposition. Then from these two propositions, we can compose a new proposition called P and Q. So this is called AND. Logical AND. Okay. So this is defined as follows. We define in terms of this table called truth table. Okay. So if proposition P is true and Q is true, then P and Q is true. Okay. If proposition P is true but proposition Q is false, then P and Q is defined to be false. Okay, so we define these values for every combination of P and Q. Okay, so if P is false and Q is true, then P and Q is false. And if both P and Q are false, then P and Q is also false. So except for the first case, every combination gives false value for this logical AND operation. So I think this is intuitively easy to understand. If P and Q are both true, only in that case, P and Q is true. Okay, that makes sense. And similarly, we can define the logical operator called OR. Okay, and OR. Okay. So let's define here. Logical OR is written as like this. Okay, so this is called OR. And so if P and Q are both true, then P or Q is true. And if P is true and Q is false, then P or Q is true. And if P is false and Q is true, then P or Q is true. If both P and Q are false, this and this, then P or Q is false. So again, this is intuitively easy to understand, I guess. So if either one of P or Q or both of them are true, then this combined statement proposition P or Q is true. Okay, these are all true. Only when both are false, both P and Q are false, then P or Q is false. The next operation is called logical negation. That is not. Okay, so let's say if P is a proposition, then not P. So this is called not. Not P is defined as follows. If P is true, then not P is false. If P is false, then not P is true. So it's just opposite of the original proposition. So we negate the proposition. So this is called negation operator. So far we have learned three logical operators that are and, or, and not. And these three operators are just sufficient for composing any kind of logical propositions. But for convenience, we define yet another operator called implication. The logical implication is defined as follows. So let's say we have two propositions P and Q, and we write if P then Q, or we say P implies Q. Okay, so this is defined as follows. When P and Q are both true, then P implies Q is true. And if P is true and Q is false, then P implies Q is false. And if P is false and Q is true, what do you think this is? It is P implies Q is true. And if P is false and Q is false, then P implies Q is again true. This may sound a bit confusing, but this is the logical consequence of implication. And of course, if both P and Q is true, then P implies Q is true. It's okay. But and if P is true and Q is not true, that is false, then it's P implies Q is false. But if P is false, then irrespective of the truth value of Q, P implies Q is always true. Okay, this means if the premise, okay, the assumption is false, then anything can be true. So this whole proposition can be true. It's true. So that's what this means. Okay, so this is logical implication. But this is strictly not elementary in the sense that this operator, implication, can be composed by using these more basic operations and, or not. Yeah, you should try by combining these three, or maybe you don't need everything, but you can actually reproduce the same operation as this one. Okay, let's see some examples. And we show that these two propositions, P and Q, not, and this proposition and this proposition, not P or not Q. So these two propositions are actually equivalent in the sense that they give the same, exactly the same truth table. So let's see it. P and Q. So we first list all possible combinations of the truth value of P and Q. True, 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 false, false, true, and false, false. Then first consider this one, P and Q. Okay, P and Q. By definition, P and Q is this one, defined as this: true, false, false, false. This one was defined before. And by combining this with negation, now we negate this, not P and Q. Okay. So this is the negation of this statement. So we just swap the truth values. So if this is true, then this is false. If this is false, this is true. And this is false, so this is true. This is false, this is true. Okay. Now, consider not P and not Q. Okay. So if P is true, then not P is false. If P is true, this is false, and false, false, so it's true, true. About Q, so this is true, false, so it should be false, true, false, true. Okay, now combine these two propositions to give not P or not Q. So by combining these two, so false, false, so false or false is false, and false or true is true, and true or false is true, and true or true is true. So now compare this and this. So this is false, false, true, 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 true. So these two propositions give exactly the same truth tables. Therefore, they are equivalent in this sense. And when two propositions are equivalent, we write with these three bars. So this is equivalent to this right-hand side. So this is actually a part of a theorem called De Morgan's law. De Morgan. And you should also show that not, okay, so this was P and Q not, okay? So not P or Q is equivalent to not P and not Q. So this is another De Morgan's law. And you should prove this by making a truth table, just like this one. Now let's consider different kind of propositions, that is propositions that depend on some variables. For example, P is a proposition that depends on some variable x. So we write that as P of x like this. For example, let's say x is an even integer. So the truth value of this proposition depends on the value of x. So for example, if x is 2, then this is an even integer, so this is true. Okay, and if we put 3 instead, then the truth value is false, right? If x is something like a cat, then of course it's not an even number, so its truth value is false. So something like that. So this kind of propositions that depend on a variable or variables is called a predicate. Predicate. Okay. And now we study how we can use this kind of propositions. Okay, here's another example. Let P of x and y, so this is a predicate that depends on two variables, x and y. So let this be x is less than y. Okay, whether this is true or false depends on the values of x and y. Here we assume that x and y are numbers, real numbers. Okay, so for example, if x is 1 and y is 2, then this is, so 1 is less than 2. That is true. So the truth value is true here. And if this is 5 and this is negative 1, so positive 5 is not less than -1. So should be false. So like this. Next, consider the following statement. Say for all x that is an integer, there exists another integer y such that x is less than y. Okay, so x and y seems to be variables, but they are in a sense constrained. That is, we have this for all x and there exists y. So these things here, for all or there exists, are called quantifiers. And in mathematics, we often use this symbol instead of in place of for all, and in place of there exists, we use this symbol. So symbolically, this statement can be written as this: for all x that is in integer set, there exists some y such that x is less than y. Okay, so this symbol is called universal quantifier. Quantifier. And this thing here is called existential quantifier. By the way we write this English sentence may sound kind of too formal, but you need to get used to this kind of expressions in mathematics. So this statement says, if you pick any integer, then you can always find another integer that is greater than the first integer x. Okay, so it's what it means is very simple. And these quantifiers just formalizes the way of writing. So it's just a simplification. Okay, so it's just so this is just rotated a. So for all, so this means all or any, for any x, and there exists. So this is upside down e. So this is upside down a. Okay, so exists for all, exists, and there exists, and so on. Okay, so this may look scary at first, but it's not. It's nothing to be scared of. Okay. Okay. Next, let's consider negation of a predicate. Let's say p of x and y means x is less than y. So what is the negation of this predicate? So what is this? So this means, so if x is less than y is negated, that means x is greater than or equal to y. Well, in mathematics, that's what it means. Okay, now what happens if a sentence involves some quantifiers like for all or there exists? Then how can we negate it? Here it is. If we negate a for all statement, so for all x in A, so A is some set and x is an element of set A. If there is some predicate that depends on x, then if we negate this, this is equivalent to the following proposition. So there exists some x in A such that not p of x is true. Okay, so this for all becomes this there exists, and this negation sign comes inside the quantifier right before the predicate. Okay, so what this means is that for all x that is in A, P of x is true. So if this is negated, then that means there exists some x in A such that P of x doesn't hold. Okay, so this is very intuitive in plain English, and that what it means here. This negation of universal quantifier. Okay, and similarly, if a sentence involves existential quantifier, there exists some x in A such that P of x is true, then if we negate this statement, then this is equivalent to for all x in A, not P of x is true. Okay, so the first statement here, inside this negation, there exists some x in A such that P of x is true. Then if we negate this, then for any of these x in A, this P of x doesn't hold. So what it means is this. For all x in A, P of x doesn't hold. So not P of x is true. Okay, so this existential quantifier becomes universal quantifier, and the negation sign comes inside the quantifier, right before the predicate. So this is how you negate a statement that involves universal or existential quantifiers. Now let's consider a bit more involved example. This is a very strange statement. You should consider what it means. It's actually a nonsense. So there exists some integer y, such that for all x that is integer, x is less than y. So what does this mean? If we change the order of this universal quantifier and this existential quantifier, then it does make sense. So the order matters. Okay, if we swap the order, so for all, let's write it. For all x that is integer, there exists some integer y such that x is less than y. So this makes sense, right? So whatever the integer x is, we can always find a greater integer y. So what this means is that, okay? But if we swap this, and to have this sentence, then it's a nonsense, okay? So what it means is that there exists some integer y such that for all x that is an integer, x is less than y. So what it means is that there exists the greatest integer, y. Okay? Actually, it doesn't. So this is nonsense. But anyway, it's okay for the present purpose. So it's a nonsense sentence. But how about if we negate it? What do we get? So according to the rule we have just explained, so first we change the outermost existential quantifier to the universal quantifier. So y for all y in Z, and then negate the inside. Okay, so then negate the inside. That is this. For all x that is integer, x is less than y. Okay, so we negate this. Now we negate this part. So this universal quantifier becomes existential quantifier. So for all becomes there exists an integer such that then negate the inside. Okay, so that's what we have now. Then if we negate x less than y, then what we have is this. For all y that is integer, there exists x that is integer such that x is greater than or equal to y. So the negation of this statement is equivalent to this one. So this reads, for all integer y, any integer y, there exists some integer x such that x is greater than or equal to y. So this is a true statement. It makes sense. So for any integer, we can always find another integer that is greater than or equal to that integer. So that's what this says. So this sounds okay. But anyway, so in this way, we can negate any statement that may involve any number of existential or universal quantifiers step by step in this way. So that's it.